Let's get started with our COMSOL tutorial today. So COMSOL is a multi-physics modeling package, and it was earlier known as FAMLab or FEM lab, where FEM stands for finite element method, and the other numerical methods utilized for modeling and most commonly used ones are finite volume method and finite difference method. So let's move on to the definition of a model. Model is a mathematical characterization of a physical system. So by which I mean that what are the mathematical equations that we want to use to describe a physical situation. Those equations could be algebraic equation, or ordinary differential equations, or partial differential equations, or any of these equations. So once we have this full set of equations that describes the physics of the system, then we call these equations our model. And this model tells us how these different variables in the system are interrelated. So let's move on to our next point in the slide. Why is modeling important? So first thing is, once we have this set of equations, mathematical equations which describe the physical system, then upon solution of these equations we exactly know how these variables behave in a given geometry or given computational domain. So model provides us a detailed understanding of underlying physics. And once we know this interdependence, then we know what are the key parameters, and we can relate those parameters to our economics, product quality, etc. Say for example, if we are operating say any chemical equipment at a flow rate of Q1 and fluid F1, and if we have developed model, then we should use it for predicting what would happen to the other physical quantities if I change my flow rate to Q2, or if I change my working fluid from F1 to F2. Then these models are useful in predicting these kind of variables behavior. And once we have these kinds of model ready, then we can use to better design our equipment or processes, and we can optimize and also use it for control. So modeling is important, and there are different ways we can model a physical system. So for example, we can use a analytical model, and by analytical I mean that if we are able to solve all these set of mathematical equations analytically, then we call it as a analytical model. And other than numerical modeling is experimental modeling, where we can directly conduct the experiment to find out the relationship between different variables. So now let us talk about these two methods in terms of numerical modeling. So numerical modeling, some of the advantages are complex and coupled physics modeling. So here I can give you an example. Say if I have a pipe, and I want to model the concentration of particular species in the system. Okay, let's denote it by CS. So this concentration, and if it is a flowing system, then this concentration distribution at any plane is dependent upon the flow rate as well as on the temperature. If the diffusivity of this species is dependent upon the temperature, so we can see that this concentration, solving for concentration, is a mass transfer problem, but this includes the effect of flow as well as the effect of temperature. So this is a coupled problem, and most of the real life engineering application problems are coupled problems, and it is difficult to solve this coupled problem using analytical approaches. So for these kind of problems, numerical modeling is very good as compared to analytical model. Also, for if we have a complicated domain, then analytical models usually are not used for these kind of complicated geometries, whereas numerical algorithm models we can use to solve such problems. Other thing is, the numerical modeling provides us detailed information, by which I mean at every point in the domain we can calculate the quantities of interest or the variables. Whereas if you compare this from your experimental modeling technique, then usually the experiment provide us very limited data. So we are looking at this advantages of numerical modeling in this case. Also, I have written here, easy to study different variations. So if I build a basic model, then once this model is ready, you can use this to study different kind of variation. For example, you can study different operating conditions with different fluid properties. All of these things are very easy once our basic model is ready. So having written down the advantages of numerical modeling, I must say that the most important part for a numerical model is validation. So we must validate our numerical model with either the known analytical solution or with the experimental data. Okay, so we have seen that numerical modeling is a powerful and relatively inexpensive technique to model physical systems. So there are several packages available to model the physical systems. One of them is COMSOL, and the few features which I really like about COMSOL are its multi-physics approach, and it's very user friendly. And other point is this complete solution, by which I means you can do all the different kinds of like you can integrate all the parts of your problem into this software. You starting from, say, defining your model, building your geometry, and defining boundary condition, meshing and solvers, and then post processing. Everything can be done in just within this software environment. So I like all of these features, and but there are different packages also available, which are every package has their own advantages and limitations. So we will see these advantages in the next couple of minutes when we start solving problems using COMSOL. So let us see the before moving on to the next slide, I would like to show you some of the animations, some of the models that we have developed using COMSOL. So the first animation I'm showing you here is a analyte band convected through a curved microchannel. So let us see it again. And you can see this effect is known as racetrack effect, where the dispersion band is let me play it again and let me stop at that point. So you can see how this band is convected and how it is distorted due to this. It is known as racetrack effect. So this is modeled using COMSOL. The flow is here is electrokinetic flow. So we have solved for electric field in this, which is driving the fluid flow. Then we are solving Navier-Stokes for momentum balance, and also we are using convection diffusion equation for solving for this concentration of this species. So we can couple all these different physics in this single software, and we can solve this multi-physics problem. And probably we're going to see some of these later in this course. So now next movie I want to show is how we can use this information to understand the physics and then design a new geometry. So in this case, the same problem, but the geometry is modified, and you can see with this optimal geometry there is not much dispersion and the band restores its original vertical position. Let us play this again. See, the dispersion is caused by this turn, and if you minimize the width of the turn, then this the concentration band is restored to its original vertical position. And similarly, we can model lots and lots of different things. Another thing I want to show is this micro mixing animation, where we have a groove micro mixer. So we have a grooves at the bottom of the channel, and these grooves generate helical flow in the systems, and this is the example where the flow is chaotic and it mixes the two species really quickly. So this is the top part, shows the cross-sectional concentration plots, how these two colors are mixing, where red initially is equal to scaled concentration of 1 and blue is a scaled concentration of 0, and when they mix, we should see a concentration of 0.5 everywhere. And so the purpose of this animation I want to show is we can really solve multi-physics problem using COMSOL. So we are in this example, we solved again the mass transfer and fluid transport. So we can use this tool to solve different kinds of problem, and all these things, post processing, everything is built in this software. So today we're going to solve some of the very simple problems that Dr. Kumar has already covered in the class, and we're going to try to solve those problems using COMSOL. So let us move on to this solution workflow. So what is the general idea to solve any problem, general steps to solve any problem? So the first part is the what is known as pre-processing step. So in this, first we want to define the model, by which I mean mathematical equations which we want to solve. So say if we are going to solve the fluid flow between flat plates, so our model is a PDE, Navier-Stokes equation. Sorry, let me write it more clearly. And continuity equation, which is the mass balance for fluid. Okay, and once we have identified the model which we want to solve, we need to define a computational domain or geometry, and then we also need to declare constants or the variables of the problem, like what are the fluid properties. Then we need to divide this computational domain into smaller elements or nodes. So say if this is my computational domain, I'm going to divide it in the finer, smaller regions, and so this is a structured mesh. So these points are known as nodes, and this complete element, so on every element, so now also we need to describe the boundary conditions other than meshing. So once we have done this, then our pre-processing part is done. Then in the solution step, we approximate the model variables by polynomial functions. So on each of these node points, we approximate our variable as polynomial function, something like this. Say where this phi I is a known interpolation function. It could be linear or quadratic, depending upon which variables we are solving, and ai is your unknown. So what essentially this does is it converts your PDE to a set of algebraic equations. And once we have this set, with using these boundary conditions, we need to solve this set of equations, which will give us the complete solution, all the variables in this domain at all the points. And once we have this solution, we can go on to the post processing step, which is to plot the quantities of interest, generate different plots, graphics, and generate animation movies. All these things we can do. So this is the general steps to start solving any problem in this. So we're going to solve the steady laminar flow between flat plate problem. This problem has been discussed in the class. So if I apply a pressure gradient in this x direction, say delta p, px here is delta px over L, which is your pressure gradient in the x direction, then your velocity profile is parabolic. And in the class we have you must have seen this derived using assuming a one-dimensional flow, but when we are solving, we're going to solve it for the full 2D problem, by which I mean we are not posing any restriction on the nature of the solution, like this u, which is the x velocity, y, which is the y velocity, v, which is the y velocity, and p. All these are function of x1 and x and x2, or x or y based on this notation, and we are not forcing it to be a function of only x or only y. Both are function of both the dimension x and y. All these variables are functions of x and y. So let us try and solve this problem in COMSOL. So just close this, and let me also close this. So where is COMSOL? It's right here. So double click this and let's open this COMSOL multiphysics. So for typing, let me cancel this. So we want to model a 2D system. It will ask for what kind of model you want to build. So let's select 2D here and then click next. Now the COMSOL has lots of inbuilt modules, so let me close this recently used and let's go over this, all of this quickly. So in AC/DC we can model electric fields and magnetic fields, and these equations are inbuilt. So if you want to model say electrostatics, then if you click this, it will automatically add the Poisson's equation or Laplace equation depending upon what you are solving. And similarly, all these physics modules are inbuilt, so you can solve mass transfer, reactions, fluid flow, heat transfer, structural mechanics problem. All these things we can solve, and we can solve them in a coupled fashion. So for this problem, let me pick this single phase flow and a laminar flow. When you click this, you can just add this, and then again click next. Then it will ask you what kind of analysis you want to do. So let us select the stationary or steady state analysis and then finish. Okay, so as soon as we click finish, it has generated a model node here which contains all these sub nodes. Okay, and it has already added this laminar flow module in this model tree. Okay, so it automatically selected this geometry point, so we need to start by building a computational domain in the system. So you can choose any of the units here to start building a geometry, and there are lots of icons here. If you click, and then you can start drawing here, but let me show you the way I prefer. So just right click this node here on the geometry and select any of these inbuilt what you want to build. Say I want to build a rectangle, so I just select this rectangle, and then you can define this length and the position. So let me say width of 10 and height of 1, and let's move this corner to minus 0.5 just to make the 0 as center line, y is equal to 0, x-axis. So once you have defined this length and width for the rectangle and its base corner vertex position, you can just click this button here for the build selected or build all. So if I select this, it will build this rectangle with the specified dimensions. Okay, so I have built the geometry, and now let's move on to this materials. You can define the any material from the material library again by right clicking and adding the material, but let us just define these flow properties by some numbers here. So let me go to this laminar flow node, and then we have it is already selected, so it's going to solve this laminar flow in this domain. And you can always click this and look at the equations. So what equations are actually inbuilt in this. So it is a Navier-Stokes equation, and then you can select incompressible flow, so it will show you the equation related to the incompressible flow. And you can also model turbulence, and there are different turbulence model available, so everything is there. But for the present case, we are modeling our flat plate flow between the flat plates. So let me choose this stationary incompressible flow, and then we go to the fluid properties part. So in the fluid properties, it asks for density and viscosity. So now again you can use it from directly from the materials, or we can define it. So just select this user define and say rho, and again select a user defined drop down from drop down menu and say mu. Okay, now we have given them name, so let us define the variables with this name. So go to this global definitions and right click and select this parameters. So in this parameter, let us give this name rho and specify a value, say 1, and again mu and specify a value of 1. So we have defined our parameters here, and we can define any of our model parameters here, and you can use them in the modeling part in any of these nodes. Once you have defined, even you can define parameters for building geometry, say length and width, and we can use it here to define the length and width of the rectangle. So we have defined these rho and mu just as one for simplicity, and to make our Reynolds number 1. So and then we have already defined here rho and mu, so our fluid properties are defined. And let's see what this node is. So if you let's fit this, and if you see this, the default boundary condition for all the walls in this module is a no slip condition. So right now by default COMSOL applies no slip boundary condition to all of these boundaries. Now if we want to model, we need to define inlet and outlets. If we are modeling this steady laminar flow between flat plate, so here we are going to, this expression is valid for a fully developed flow, so where we are neglecting entry and exit effects. So this can be modeled in a different way. So we're going to use a periodic boundary condition to model this case. So in a periodic boundary conditions, we choose a source cross section and a destination cross section, and the velocity profile at the destination is same as the velocity profile at the source. So it means whatever flow is here, it is again same flow is applied at the inlet also. So it is like a fully developed flow assumption, and we are neglecting the entry and exit effects in this case. So let us apply this boundary condition, and this is inbuilt. Again, go to this laminar flow node and right click, and then we can add a periodic flow condition here. Okay, in this periodic flow condition we need to define which phases are we need to apply this condition at. So let us select this phase and then press Ctrl and Shift, again select this, and then you can add using this plus sign to the selection, and COMSOL automatically knows which one is destination. So you can also right click and add a destination selection. So right now it is considering 4 as destination, and also we need to define a pressure difference to drive the flow. So for this case, let us define a pressure difference of 10, so that our pressure gradient will be 1, because our width of the channel is 10. So we have defined pressure difference, periodic boundary conditions here, and now if I go back to this node, then you can see now these inlet and outlet boundaries 1 and 4 are overwritten, but the boundary 2 and 3 is still have a no slip condition, so which is good. So we have defined our geometry, we have defined our model, we have defined fluid properties, we have defined boundary condition. Now next part is to mesh the problem, mesh the domain. Okay, so let us look at this mesh. So we have different options. We can create different kinds of elements. So but let's start with the inbuilt mesh. So again, there are different types here, extremely coarse to extremely fine. So let us choose, say, coarser mesh and create this mesh. So in the messages you can see this mesh contains roughly 3700 elements, and the more finer mesh you choose, we have more number of elements and the solution will be more accurate. Okay, so let us for time being use this coarse mesh. So we have defined our mesh also. Now let's see what's inside this node. So in this study node we have the solver details. We can add solver to this by right clicking this study and say show default solver. Okay, so there are different solver choices available to us, but for this problem let's just stick with the default solver, which is a direct solver in this case, and it is using Pardiso solver here. So it's pretty much set, and we can solve this problem now. We have defined what is needed to solve the problem. So let's just right click this node study 1 and click compute. You can see the progress here, error, and you can also click this log and progress. So what it says is it gives us a error which says fail to find a solution. But if you look at this velocity magnitude, and it looks like it has solved something, and if you go back to this log, and if you see the error is low, but it ran out of the number of iteration. The default number of iteration is 25 in this case. So the problem in this one is, again, we have defined a pressure difference of 10. So our pressure gradient is 1 in this case, which we have defined in the COMSOL. The problem is we have not uniquely defined our pressure profile, by which I means we have just imposed the delta P of 10. So but this delta P of 10 can be imposed in many ways. For example, we could have a pressure of 10 and reference pressure of 0, or a pressure of 20 at inlet, pressure of 10, or lots of combination like this. So this kind of non-uniqueness to the pressure profile causes this kind of convergence error in COMSOL, but it can be fixed by just imposing or constraining pressure at any point. So that also can be done by going to this flow and adding a pressure constraint to this. So let's go to this right click laminar flow, go to points and add a pressure point constraint. So once you add this, again you need to add a point. So let's just pick this outlet point, add to this selection and declare a pressure of 0. We can declare any value here, so let's just keep it 0. So we are just giving a reference value to pressure at this point, so that it will fix this problem. So with this added condition, let us just again compute the solution. And see, now it doesn't give us any error, and you can see the error also goes to 2 to the power of minus 10. So we have solved this problem, and now let us compare this solution with the analytical profile that we have for the velocity. So for this we need to construct a data set. Say if I want to plot my velocity profile, we want to construct a line. So right click this data set and select a cut line 2D. So in this cut line 2D, say x is 5, this is also 5, and say y is from 1 to minus 1. Once you have done, you can click this to see the location of line, and it shows it is the center, vertical center line. Similarly, we can add a horizontal line at the center line. So again, right click data set, add a cut line 2D, say x 0 to 10 and y is equal to 0, and again click plot to see. And you can also rename this by again say right clicking and say rename, and let's put this as center line in the x direction, and let's put it as this, rename it as center line in y direction. Okay, so we have defined these two lines. Now we can plot any of the quantities for which, any of the variables which we have solved on these lines. So let us again right click on this, right click and select a 1D plot group. In 1D plot group we need to select the data set. So let us select this center line in the y direction. Okay, again right click this plot group and select a line graph. In this line graph, the expression already written here is for the magnitude of u. So let us just plot this. Okay, so it shows a parabolic profile along this cross section. Okay, and you can see it is not fully parabolic but slightly distorted, and that is due to the your mesh. So when we have larger gradients, we need to use a finer mesh. So since we have used a coarse mesh, we do not see a fully parabolic profile, but it's kind of distorted. So let's go back and quickly select a little finer mesh. Instead of coarse, let's go to the normal and redo the mesh thing. And if you go to the message, now it has almost 4 times element what we had earlier. So with this, let us again compute this problem, and Now let us plot this. So it is not that distorted that we saw it before, and let us also plot the analytical solution in this. So right click this and add another line graph in this one. So analytical solution is 1 over 2 mu px. So in our case we have declared mu as 1. Our px by definition is also 1, and so it is y square minus h square, and here h is the width is 2h, so in our case the h is 0.5. so let us remember this and plug it into the COMSOL plot. So it will be 1 over 2 y square minus 0.5 square. So let's go back here. So this for the second line graph, let me put this expression 0.5 times your pressure gradient is 1 by definition, so it is y square minus 0.5 square, and then just click the plot. Okay, now if you see, it is the red line is the second plot, analytical solution. So again you can, let us quickly rename these. So select this numerical which we have solved, and then rename this, right clicking and say analytical, so that we know which one we are talking about. So in this one it is also showing parabolic, but in the exactly opposite. So the problem here is we have used a pressure gradient of 1 in our this expression in COMSOL, but the pressure gradient is -1 because pressure is decreasing in the direction of flow. So final pressure is 0 and it is 10. So let us just go back and make it pressure gradient -1, and if you plot now, then your analytical and numerical solution matches well. So just to summarize, we have built a very basic model using periodic boundary condition, and the flow solution matches well with the analytical solution. Let us look at the pressure profile. So add another 1D plot group, and again select this time the center line X. So now we are plotting our data on this horizontal center line. Again select a line graph, and in this line graph we want to plot the pressure. So pressure here is defined by P, and you can always click this button and see the inbuilt definition. So if you go to laminar flow, it will tell you pressure is defined by P, velocity magnitude is defined by SPF dot mu. Here SPF is your module identifier, which is single phase flow dot u. So these are all inbuilt quantities which you can plot directly, and other quantities you can define it as in terms of these quantities and plot. So let us just select P and plot, and you can see a linear pressure drop which is expected in this problem. So again I want to emphasize on 2 points. First thing is, we have not imposed any restriction on the on these variables that the velocity is one-dimensional. We are solving a full two-dimensional model here. And secondly, these results are affected by the mesh quality. Okay, so let us do a quick variation on this. Instead of periodic flow condition, if I impose a flat inlet velocity, then what would happen? Okay, so to study that, we can just disable this periodic flow condition, and also let us disable this pressure point condition. Okay, now we need to again define inlet and outlet. So right click this and add a inlet boundary condition, and select this boundary as inlet, and right click here, it will be added to the boundary selection. Then again go to laminar flow, add an outlet. To this outlet, we want this boundary to be outlet, and no, not this one but this one, and again right click, it will be added to your selection. So at this outlet we have imposed a 0 reference pressure, and at inlet we have a normal inflow velocity. Let's give it a magnitude of 1. Okay, so we have given this magnitude of 1, and so when we impose a flat velocity profile at this inlet, the flow needs a finite length to achieve a parabolic profile, and that length is known as entrance length. So, and now this entrance length changes with the Reynolds number. Okay, so let us try to do a parametric study. So we have defined rho as 1. So if I increase my density rho, then my Reynolds number is effectively increasing in the system. So let us do a parametric study with reference to our this parameter rho, which is fluid density. So go to this step stationary, and in the extension we can do a continuation, and in this add we can add which parameter we want to select. So select rho, and then we can define different values, say 1, 5, 10, 25, 50. Okay, so we are increasing the density, and so in a way we are increasing the Reynolds number. So once we have done this, let us again right click this and compute. Okay, and let us go back to this. So it has solved for all of these different 5 parameter values, and it is showing a solution for this 5th value of rho, which is 50. Now we need to zoom in here and see what is happening in the entrance region. So if you go there, you can see that flow is not parabolic here, but it takes a finite length to achieve a parabolic profile. Okay, so and let us go here and plot it for a different parameter value. So if you plot for 1, then you can see it needs the entrance length is smaller. So we can plot this also. So let's go to this plot, and let us select SPF.u, velocity magnitude, and if you plot this, you can see the length where the magnitude is reaching its maximum value of 1.5. so we can see as we are increasing the Reynolds number, the higher the Reynolds number, the more the entrance length is. Okay, so we can study these kind of parametric studies with respect to one or more than one parameters, and these parameters could be your properties or they could be geometric parameters. So we can study these kind of things. Okay, so let us also quickly look at the velocity profiles. So let me go back to this surface plot. Okay, and let me add a arrow surface. So we are plotting u and v, which is the x component of velocity and y component of velocity, and you can select number of points and say let us reduce the y number of points to 10, and okay, let us see. So let's make this background more uniform color. So go to the surface, and in this coloring and style, instead of color table select uniform, and instead of red select maybe gray. Okay, So now our profiles are more visible, and let's see the entrance region. Okay, so you can again right click and drag this like this. So flow is, this is for the rho is equal to 1, so your velocity attains its parabolic shape very quickly. But now if I plot the same graph for say 50, and then you can see the difference. Okay, so again we can use this to plot any quantities of interest, and the post processing is really good in COMSOL. We can do lots and lots of things in the derived values. We can do all kinds of these averaging, integration to find out the flow rates across any cross section at the outlet. All of these things can be done. So let us do another quick variation on this problem. So let us do a moving plate problem. Okay, so now let me go back here to this inlet, and let me define zero velocity at the inlet, because we just want to model the flow due to moving plate. And now let me add another wall condition. In this wall condition, let us select this boundary and right click. It will be added to your selection, and in the boundary condition, instead of no slip, let us select a moving wall. Okay, and let us say now this top plate is moving in the x direction with a velocity of 1. Okay, so we have defined the wall condition, and then inlet and outlets are at reference pressure. So let us put this boundary as also reference pressure, and with this let us just compute the solution. Okay, and it has again solved for all of the row values. Again it solved for the parametric different row values from 1 to 50. Now you can look at this velocity profile. The fully developed profile is a linear profile, and let us also go back here to look at this profile. So this is linear, and remember this, our analytical solution is from the previous parabolic profile, that's why it's not matching. But we know that if you go back to this slide, and we know that we are modeling only this part when we have a co-wet flow where the fluid is moving due to this moving plate. So the velocity profile is linear, and that is what we have observed in our COMSOL simulation. So this part is, so we can use this to model this fluid flow. And once you get this basic idea and start building this basic models, then you can add multiple physics by again right clicking this, and then you can add mass transfer and heat transfer to this flow problems and solve a fully coupled problem. So let me save this model, and let us move on to the flow in a circular geometry, circular tube or a cylinder. So let me save this quickly. Save as flat plate flow. Okay, and let's now look at this problem. Our steady flow in a cylindrical pipe. So now this we need to model the flow in a cylindrical pipe. So this 3D cylindrical geometry we can approximate using a 2D axisymmetric approach. So if this is our r is equal to 0 and this is your radial direction, this is your z direction. So if I draw a geometry like this in a 2D axisymmetric mode, what I mean is if I rotate this rectangle along this axis, then it will generate the same cylinder. So it's a circular symmetry along this theta direction. So because of this symmetry, we can use a 2D axisymmetric mode and model the same thing. So let's go back, and instead of selecting 2D, let us select a 2D axisymmetric. And again, same procedure, click next, and we have used it, so let us select this laminar flow, click next, and again we are going to study the stationary laminar flow in a circular pipe. So we have selected stationary and finished this. So now it's a repetition of what we have done earlier for this flat plate case. So let us quickly build a geometry by right clicking and adding a rectangle, and say width of 1 and height of 10, and build this one. So this is our channel, okay, and this is your axis of symmetry, r is equal to 0, this line. And so we have built our geometry. Let us go back to our fluid flow module, and in this let us define it as incompressible flow, and go back to the fluid properties, again define it as say 1, and mu also as 1, okay. And so because it is 2D axisymmetric, this axial symmetry condition is imposed here, and all the other walls are at default no slip condition. So let us, and this initial value is used for time dependent problems, but since we are solving a steady state problem, we don't need to worry about it right now. So let us again add an inlet, and let us define this by clicking this boundary and right clicking here, and let us define a inlet normal velocity of 1. Again right clicking this node and adding an outlet, and let's click this boundary and right click to add it, and let us define it as a 0 reference pressure. And there are a lot of things we can add. We can add volumetric force term, which if you go to this laminar flow equation, you can see this external body force term is here, which we can add again from this node, and we can define gravitational force or electrokinetic force. You can use it to define these additional forces and see their effect on the fluid flow behavior, but right now we are not considering these forces. So we have defined all the boundary conditions for this model. Let us go to the mesh, and let's go with the normal mesh, and it is roughly 8500 elements. So again go to this study, right click and compute. Okay, so again let us compare our solution with the analytical solution that we have. So in this case the solution is 1/4 mu p z is the gradient in the z direction, r square minus r is the radius. So let us go back here and let us build a cross-sectional line, a data set. So click a cut line 2D, and we want to go it from 0 to 1, and from say at z is equal to 5, a midpoint. Again, you can click this to see where this line is. So we want to now plot our velocity at this line to see if it is parabolic and it matches with our analytical solution. So we have defined a data set, a cut line data set. Again, now right click and add a 1D plot group, and in the data set select the cut line 2D. Now again right click this and select a line graph. In this line graph we already have a magnitude, and we can click this. So it's a parabolic, but note this maximum value which is appearing at the r is equal to 0 center line is 2. So and we know that in a circular pipe or in a cylindrical pipe, the maximum velocity has magnitude twice of the average velocity. In our case, the average velocity we imposed is 1. So let us also quickly add another line graph to validate with our analytical solution. So let me quickly rename it as analytical solution, and this one is, the first one is numerical. So let me also rename this for clarity. Numerical. Okay, now what is the expression here is 1 over 4, so 0.25, mu is 1, pz, the gradient in the z direction, we do not know. We need to calculate this from the inbuilt variables in COMSOL, and r is equal to 1 here. Okay, so let's go back and plug this in. So in the analytical expression, I'm going to write down for 1 by 4.25 times the, now what is the gradient in the z direction for pressure? We denote it by p is your pressure variable, and followed by the z, followed by z denotes, so pz denotes the gradient in the pressure gradient in the z direction. Similarly, if I write pr like this, it denotes a gradient in the radial direction. So let us use pz, and also we need to use the remaining terms is r square minus our radius is 1 square is 1, so I can leave it like that. And so let us plot this. Okay, so now you can see that the analytical solution is okay, but there is some problem here. It is not matching well. So our solution is not correct. So we can improve this. So it allows us to look at one more additional feature. So let me tell you what exactly is happening here. If you click on this show and see the say discretization, and now if you go to this interface and click on this discretization, so right now we are using p1 plus p1 scheme for discretization here. So as I told you before, we are representing these variables by polynomial functions. So these functions, this is the degree of these functions. If you are using this linear shape elements or linear interpolation functions, then this function is a linear. We can use a quadratic function here also. So with as we increase the degree of these polynomials, the accuracy increases. And for standard flow problems, we use p2 p1 scheme, which is quadratic elements for the velocity and linear elements for pressure. So let us just go back, and instead of this P1 plus P1, let us select this P2 plus P1. So all we are doing is just selecting a more higher degree polynomial to represent our variables at these discrete node points. So with this P2 plus P1 kind of discretization, let us solve the problem again. And so we have solution, and let us go back to this graph again, and now you can see your analytical solution and numerical solution both matches well. So with the higher order polynomial function, our solution is more accurate, and usually for fluid flow and chemical engineering problems, our quadratic elements are typically used. So our solution is now well matched with this. So let us do one more quick problem, and I'll save this problem. So let me save it as pipe flow. To the axis symmetric and save. Okay, now let's see, let's do a problem with some different geometry. So click new and select a 2D planar flow. Click next, select laminar flow, single phase flow SPF. Again click next, use stationary and say finish. Now let us focus on our geometry here. So we want to build a tapered geometry. So let us say I want to build this kind of geometry. Okay, with this is x is equal to 0, and say this is your y is equal to 0. So let us write the coordinates for this. So this is your this is y is equal to 0, this is x is equal to 0, y axis, x axis. So I'd say this is 0 comma 1, 0 comma minus 1, and say this point is 10 comma minus 3, and this is 10 comma 3. So we have just written down the coordinate xy coordinates for these 4 points. So let's go back, and in the geometry right click and say we want to build a polygon. Okay, so now we just need to give this vertices in order x and y coordinates. So let's go from this 1 2 3 and 4. So our x is 0 0 10 10, and y is minus 1 1 3 and minus 3. Okay, so let's go here and write x is 0 0 10 10 and y as minus 1 1 3 and minus 3. So we have defined coordinates for our polygon, and then just click the selected and you will see this polygon. So there are lots of different operations that you can do with this when you're building the geometry. For example, if you can create, if you right click, you can do all these kinds of Boolean operations where you can, if you have created more than one geometric object, then you can do difference, union, intersection, and or different kinds of operation. Other operation you can do is you can array, copy, mirror, all these things. So let us just say you want to mirror this, or you want to say okay, let's do mirror. So when you select mirror, so you'll select the object and add this the object you want to mirror. Okay, and then you need to define the point on line of reflection and normal vector to the line of reflection. Okay, so let us mirror along this line. Okay, this boundary. So point on the line of reflection will be your 0 0. Okay, and normal vector to the line of reflection is, if I say x is equal to 1, so it will be a normal vector. So let us say normal vector as -1, and then say build all. So what did it do? Okay, so it mirrored the geometry, but then we did not check this keep input object. So let us do this and again select this, and now you can see the full geometry. So we have, initially we build only this part, but then with the mirror operation we have mirrored this geometry and build it this geometry. Similarly, you can use all these different functions, which are, say, you can create array, and it is particularly useful when we have similar structured repeating units. So all these operations are very useful. You can rotate, design, scale, all these things are very useful in this one. So let us just solve a quick problem within this channel. So we have this geometry. Go back to this laminar flow, fluid properties. In the laminar flow, let us define the incompressible flow and fluid properties. So just see, now we have two domains here. So you can also make a union by going to this and click this, but this is also okay with two domains. So let's just go here, user defined function, define the fluid properties as 1, and then viscosity is also 1. Okay, and by default there's no slip condition everywhere, so let us just add the inlet and outlet. So adding inlet, I'll select this boundary and right click, and let's define a velocity of 1 here, and then I go to again the laminar flow, click outlet and select this boundary as my outlet, right click here, it will be added to the selection. And with this 0 reference pressure, let's select a normal, let's go for coarse mesh, select. Okay, so you can see the mesh type, and for accuracy we can increase the mesh, and there are lots of different types of mesh in this. If you right click, you can see there are boundary layer meshes, mapped meshes, quad meshes, triangular elements. So all these things are different meshes, have different purpose, and probably we'll going to see some of these in our later tutorials if we get time. So for time being, and also what I want to mention is you can define these number of elements along the particular edges or minimum size. So we always don't need to go with this default settings or default mesh types. We can customize all these meshes, but let's just go with this mesh for time being. So with all these model, boundary conditions, fluid properties and mesh, let's go back to this study and compute the solution. As you compute the solution, you can see, because of the continuity, this area is where the area is minimum, the velocity is high, following the mass conservation of fluid. And let us look at the pressure profile. So if I again add a data set, cut line 2D, and now it needs to go from -10 to 10. So let me write -10 and 10, and let's see where this line is. So we want to plot pressure along this line. So right click on the results, add a 1D plot group. In this 1D plot group, select the cut line which you have defined, and then right click this to select a line graph. In this line graph, let us look at the velocity magnitude also. So if I click, it will show you that initially it is 1 and then it is increasing at this arc length of 10, which is equal to x is equal to 0. So you can also select this x-axis parameter instead of arc length. You can select the x or y, whatever you need to. So let us select this expression and give this expression x and replot. So now you have the coordinate. So it is maximum at this x is equal to 0. Okay, so let us now try to look at the pressure profile in this case. So if you click pressure, you can see a non-linear profile because of the geometry, which is also expected. But this solution is not accurate because we are using a coarse mesh and also only P1 plus P1 kind of discretization. So again we can go back and choose a higher order discretization. So let me select this discretization, go back here, and in the discretization let's select P2 plus P1. In the mesh, let's go for a fine mesh and say build this, and let us recompute by right clicking the study. Okay, and let us see the line graph of velocity SPF dot u magnitude. Okay, so now we want to know if our mass is conserved in this case. Okay, so let us integrate to find out the flow rate. So for this, integration can also be done by defining a cut plane. So let's define a cut line in this case. It's the 2D case. So cut line, let's define a cross section at x is equal to 0 and y going from say 5 to -5, and let's see this. So this is this line in the center, and at this line right click this derived value and you want to integrate, you want to perform a line integration. In this, select this cut line 2D and you want to integrate the SPF dot mu expression for your magnitude. So if you select this and say calculate, it is showing a velocity magnitude of 5.98 here. So this is your flow rate. Remember, we are modeling it in 2D, so our it is flow rate per unit width, per unit depth, which is the third dimension. So this value is 5.98. And what is our initial flow rate? If you look at the initial flow rate, so this is our inlet, which is value of 6 units, and we are imposing a average inlet flow of 1, so it's roughly 6. So at this inlet our mass is approximately conserved. The flow rate at inlet is 6 and the flow rate at this plane, this line, is 5.98, which is close, and we can further more accurately do this by increasing our mesh or increasing the solution. So similarly you can find out this average values, and you can define this integration along any of the lines that you can define in a data set. So other than line integration, we can do lots of different things like averaging, maximum, finding a maximum value, minimum value. All these things can be done. Okay, so uh, basically we'll end this tutorial with this model, and if you have any questions you can either write me an email or come to my office, which is room 292, or you can ask Dr. Kumar. So let me know if you have any questions. Thank you for your time and attention.